So again, I just want to highlight Shrek sucks. Okay. The first one didn't save, so here we go. Okay, today we get to start 4.7. And 4.7 is a doozy. Not that it's particularly challenging or any more challenging than other stuff that we do. I actually think it's way cooler because it's nice and applied. This, in our class for 4.7, I'm just trying to see what they say, is a 5-day lesson, which is pretty much just 5 days of problems, just like with related rate stuff. So here we go. When we see this, because I'm going to define it right off the bat, I guess we'll just define it here. Our focus is entirely, and I'm going to define it right here, on the idea of optimization. Now, if I'm a business or I own a business and I want to optimize my sales, what does that mean? What am I trying to do? I want the maximum profit. What am I doing if I want to optimize my costs? Weird. I want the minimal. I can't speak. I want the minimal, right? Like whether I'm optimizing for minimum or maximum depends on the context. Okay. Now, as we do these, all optimization is, and you should have done a little bit in Algebra 2, but I didn't teach you Algebra 2. It is simply the process of finding the best. And I'm going to put that in quotations. The best, or a more natural word, optimal solution. And again, it depends on the context. Nobody ever thinks, I just want to spend somewhere in the middle. They want to spend the least amount of money if they're trying to make it money, right? Like naturally, that's what we do. So as we're dealing with this, there's a million different contexts we could apply to business, min and max, to production. The minimum material to make the maximum volume is a question that I posed at the start of class. And it turns out that you guys had, at the start of it, at least a beginning approach to it. We need to be able to find derivatives of stuff because we're looking for the extrema. So whether we use the first derivative test or the second derivative test to determine that extrema is irrelevant, but we just need to find it. So when we're setting these up, I have some guidelines that I think are going to be helpful, but just like every time we have guidelines, they're not set in stone. These are just suggestions for things that, hey, you should try these things. We might vary a little bit from what we're about to say, but predominantly it's just this. So here we go, solving these problems. So solving probs. Okay, this one, I'm not going to write it all. First thing you have to do, you got to read it. You have to read your problem in full, and I'm guilty of reading the first part and starting it. I try to resist. You guys should do the same. Read the problem in full to make sure you really understand it. From reading it, the most important part, and these are numbered, well, I have them as numbered. Step 1, after you've read it, you want to identify the quantity. Identify. I'm too bold here, I don't know why. Identify the quantity we are optimizing. So this you guys all had as I was coming around looking at your pages. On that box example, they got cut out. So Angel, you'll just have to ask about this. The box example that we saw, we were trying to optimize which quantity? The volume. We were trying to find the biggest volume, right? The maximum volume. And as I was coming around, I saw you guys had V equals and you started calculating out volumes. That's awesome. What you didn't do, I don't think necessarily, is sum of part 2. And this is like the key to solving these problems. We want to assign symbols or variables is the more natural word. Assign variables, which you guys did. You used L, W, and H is what I saw on most of your pages. We want to assign variables to other quantities that we might have. Now, this one, it just depends if we're given other stuff or not. If we have to think about other pieces, we need a way to represent those, naturally, if we're going to write it down mathematically. Now, most helpful with this, about half of you guys did. If it's possible, and it won't always be, but it's very much like geometry. If you are trying to do a problem in geometry and you're just looking at it, what's going to help you with the geometry problem? or a physics problem oftentimes. What did we do before we started doing the math? Label, you write down what you know. That's like this part 1 and 2. But there's one other thing that's pretty helpful. Let's draw a picture. And Sean, what were you going to say? Because I bet it was also helpful. Yeah, so we identify all the stuff that we need, what we're given, but we also should draw a picture to help us relate variables. So this is imperative, whether you're doing physics, you're doing related rates, the picture will be helpful. We need a way to relate these things, and I'm going to say vars for variables. We need a way to relate them all together. Now, the last little part, and this is where it can get a little shaky sometimes, but we need a function to actually be able to deal with, right? If we're going to take a derivative, I don't just say dd. We always say ddx or ddt, whatever the case is. We need a variable that we're going to differentiate with respect to. If we want to be able to find the derivative, it means we need an expression that has just a bunch of that variable in it, right? We could do implicit, maybe, depending on the situation. But for step 3, our main goal, and this might take 3 and 4, depending, we want to express the quantity we're optimizing. Express the quantity we are optimizing as a function of one of the variables. Now, there's one more little part on this, but all that means is when we do the box problem here in just a minute, we had to cut a square out of each part, right? And the piece that nobody had is that I didn't see, so maybe you did have it, but how big was the square you were cutting out? If you don't know, what should the dimensions of that square have been? We could have said it's x by x, right? And then all of a sudden, we have a way to talk about the length with an x in it. We have a way to talk about the width with an x in it. We have a way to talk about the height. Everything is in terms of x, and we now have something that we can differentiate with respect to x. Like, that was the goal. In this situation, what might happen, and it's a weird part, I'm going to make that a comma. The other part that we want to think about is the domain, and determine appropriate domain. Now, this is not always super duper easy, but I just want to give an example of this. Does it make sense for me to say I'm going to cut a square out of each corner that has a length of -2? That's nonsense, right? Like, the function that I write could have a min or a max somewhere in the negatives, but if it doesn't make sense in the problem, why would we use it? So we need a realistic domain so that the x or t, whatever variable, actually makes sense. Okay, the last thing is step 4, do some calc. And I'm going to be more specific. Find min and max is what I'm really going to say. Find min or max. And we'll even add it in with calc. Okay. Now, as we go through these, we are not going to have homework tonight, but we have about 10 minutes left. I think we have time to knock out that box problem and at least start it to a point where you're going to be able to finish it. So let's do that now. We're going to jump right in. You do not have to write down this whole thing, but I do want to start this problem. You don't have to write this down. We're just going to put the dimensions on it right off the bat, and we'll just draw a picture to make sense of this. So if I give you a sheet of, this is metal in this case, but if I give you a sheet of paper or metal, what shape is it right off the bat? It's rectangular. So I'm going to draw the picture right here. And here's my rectangular sheet of paper. And I'm not drawing it to scale. That's okay. Here it is. Before I cut any of the squares out, I don't really care which one, but what's this length? 10 inches. And this length, and I'm going to scroll down just a skosh, this length here was 15 inches, right? Okay. I'm going to cut stuff out of this. And specifically, we're going to cut little squares out. And I have to draw them to some specific size. And I don't know if this is really the right size or not, but it doesn't matter because I'm not to scale. These are the cuts that we would make, and they're cuts that I made on the piece of paper to fold up a box. Right now, the goal is, how do I find how big that square needs to be, right? So I don't know this length, but what could I call it? This is X, and I would just put one of them. But do you agree that if that's X, then so are all of these? And you don't really have to label all of them. I happen to have a lot of space on mine, so I can't. Did any of you guys have a length on that little square? Because a lot of you guys did have the squares drawn, which was awesome. Did anybody have a unit on it? So X. Okay, so we'll get there. Okay, so looking at this, do we all agree that this picture kind of summarizes everything? Now, really all we're trying to do is, and just so that you guys don't have to write this whole thing, from this picture, and we can just call this example A, you can just say find max volume. Find maximum volume. Now, in this one, it is pretty easy to set this one up. There's nothing crazy that goes on. We're trying to maximize the volume, right? So here's what we're going to do. We're going to think about these, and right off the bat, you guys had this. Step 1 of our step-by-step process says read it. Let's pick something to represent that quantity we're trying to maximize. How are we going to represent volume? It's a capital V, right? Now, it's going to feel weird this time, but I'm going to switch to, not the orange part, that's not what feels weird. I'm going to start with what's called a primary equation. Now, we won't even need anything else in this one, I don't think, but we have a primary equation. This is the thing that we're trying to optimize. And you guys just told me, but I want to hit it again. It's we're optimizing what? Volume. And how do you find the volume of a box? So right now we can say it's length times width times height. And most of you guys had this. Here's the issue that we run into and what prevents us from actually solving this problem. If I asked you to take the derivative of this, right off the bat, it's we don't even know what it would be with respect to. And I can do the left side, it's no problem, B prime. But I can't differentiate these. Like I can't just say it's L prime and W prime and H prime, because that's not how product rule works. I need a way to work a variable in here. Now, whether this stays consistent in being, like it won't stay this simple every time, but I'm going to refer to what we're going to write here. We're going to make it look the same. I'm going to write some secondary stuff as well. Now, if we wanted to be really thorough, secondary equation or tertiary or quaternary would just be the second, third, and fourth. I'm just going to call them all my secondary equations. So from this picture, if I said, hey, let's write these with a common variable. Any thought on the variable that I can use? Because the length isn't just 10, is it? What's the length actually equal to in this picture? So let me rephrase. What will the length of my box be? Not the length of my sheet of paper, because it's going to fold up, right? If we fold up here and here, it's no longer 10 wide, is it? It's 10 minus, that part is no longer counted, and that part's no longer counted. It must be 10 minus 2x. Because each side had a piece of length x that folded up and took away from my length. What's the width? 15 minus 2x. And then this is the weirdest part. What's the height? Awesome. Good call. It's just x. Now, what we have done is we just assigned all the symbols to the secondary things, right? All the other variables. We needed a way to write L and W and H. We now have it. What I can do now is I can substitute these in. And I now have a way to find volume where I only have a singular variable. Instead of just writing V equals, I'm going to write it very specifically. We now, combining these two, can write a function. So all of this right here, combine, it takes us to not just a volume anymore, but we get volume in terms of what? We get a volume in terms of x. And instead of length times width times height, I'm going to change it so it's height times something. So I can write the x first, times 10 minus 2x, times 15 minus 2x. We now have an expression for the volume of this box that is entirely dependent on the x that we choose. Do we, at the same time, now have a function that we can take a derivative to, and very clearly a derivative with respect to a variable? Now, would you stop here? Do you want to do the product rule 3 times, or is there a little bit of stuff that we can do to make this a little nicer? Could everybody, can you expand this? Do you need the practice to expand, or can I just tell you what this expands to? Okay, I'm good with that. This thing will expand to 4x cubed. And there's a ... that should happen to show that I didn't do this in my head. I would just do it on my calculator. 4x cubed minus 50x squared plus 150x. That is the expansion of that multiplication. Okay, at this point, this one, you will not always get burned if you forget it, but we now have it expressed as a single function in one variable. That's nice and handy. Are there values of x, my domain, that I might want to consider here? Because if I look at this function, I think that there's probably going to be an extrema left on the negative x-axis somewhere. What x's don't make sense? Yeah, note, if we want this box to actually become a box, we have to have x greater than what? 0. So any critical number that we find that's less than 0 or equal to 0 is garbage. We don't even need it. You can't make a box if it doesn't have any height. Okay, here's my challenge for you. We have about 80 seconds left in class. You might be able to finish in 80 seconds. I want you to find the maximum of this function. Now, nothing new. You don't even have to graph it. Your job this evening is to do very similar to what we did in previous sections. Find the x that maximizes volume. I think that if I'd given you guys more than 5 minutes and a little bit more of a nudge, this picture would have been able to get it. I think so. Cool. That's your assignment. Now I'm going to try my very best. Do not forget, I'm going to count this as an assignment tomorrow. Not right or wrong, but I am going to come around at the start of class tomorrow and actually count it as a homework. Finish this problem. Cool. Sweet.